Hello and welcome again to Physical Chemistry for Life Sciences. We are continuing with chapter 6, which is the rate of the reaction. And today we are going to talk more about the rate and the integrated rate laws and some important stuff in this chapter. From the last lecture, we have introduced the idea of the rate, which is just like the speed of the car. The speed, instead of saying the speed is equal distance over time, in chemistry the rate is concentration over time, or basically change in concentration over a change in time. Now, at any point in this curve here, when the reactants are actually depleting, we can define an instantaneous rate, which is the rate at any of these points here, at the beginning, at the middle, or at the end. At any point, at any time, you can actually take the tangent of that curve, and you can determine the instantaneous rate. What we are interested in chemistry, actually, and chemical kinetics, is the initial rate, which is the tangent of this curve at the very beginning of this reaction, and we call this the initial rate, okay? And we're going to use this today as a rule. We also talked about the relationship between the rates for the reactants and products and the negative and the positive sign and all of that. And we define the rate law, which is it takes the general form of V, which is the rate is equal Kr, which is the rate constant, times the products of the reactants. I mean the multiplication of reactants. So A power M, B power N, C power whatever. That's a general law of the rate reactant. The rate law, it is composed of three things. First, the V, which is the rate, and this is called the rate of reaction. It always has units of concentration divided by units of time, and it could be like molar per second or more liter minus 1 second minus 1. It could also be units of concentration like pressure over time, okay? The Kr, the rate constant, it's a constant, it's only affected by temperature, so whatever you do with the concentrations of A and B, Kr, it stays as constant. It's unsimilar to the equilibrium constant, which is large K. It has units, this one has units. So, and its units are written in a form to equalize this equation. So, and therefore it has different units, whether it is first order or second order or so on. M and N are called the orders of the reaction, and some people, they call them by mistake the order of the rate. There is nothing called the rate of the orders of the rate. These are the orders of the reaction. So if M is 1, then we say this is first order in terms of A. If N is 2, then we say this is second order in terms of B, and the total would be a third order, of course. And we mentioned last time that also A and B, M and N can also be fractions, like half or 1/3 or whatever. The M and N are the rate orders, or the reaction orders are only can be determined experimentally, and we cannot actually determine them from the equation itself. We also talked about the Kr and so on. So today, if we are saying that the orders or the rate law can only be determined experimentally, let us introduce you to some of the experimental methods that we use in chemistry to determine the rate law. And the first one is called the isolation method. So the isolation method is really simple. If you have two reactants in A and B, we can use an large excess amount of B, and therefore we can assume that B is constant, and therefore the rate law, instead of saying V is equal Kr A power B, we take that B to be a constant, and therefore we have two constants, which is the Kr itself and B, and the reaction becomes V is equal Kr prime times A, and this is called pseudo first order kinetics. And the word pseudo, as I mentioned in a previous lecture, means like as like, okay? So it's like first order reaction. It's not actual first order, but it's like first order reaction. And the Kr prime here, we call it the effective rate constant, or the apparent rate constant that we observe from the experiment. So keep these two equations in mind. We're going to use them in when we solve problems. Now, the other method that we are it's widely used, is the method of initial rates. And in this method, what we do is we carry a few experiments on one of the reactants by changing its concentration, and we determine the initial rate for A from the graph, as I showed you before, at different concentrations. And then we make a graph, and from the graph we can actually determine the value of the A, which is the A small, which is the order in respect to A for the reaction. So this method is usually used in combination with the isolation method. So if you take that equation after we separate B, the rate law becomes V is equal Kr prime times A power A small, where A small is the order in respect to A. You can name that M or N or whatever. At the beginning of the reaction, this becomes V naught is equal Kr prime times A naught times A. If you taken logarithms of both sides for this equation, the equation becomes log V naught equals log K prime plus A log A, and this takes the form of a linear straight line equation or linear equation in the form of y equals mx plus b, or y equals intercept plus b. Let me just show you how this happened mathematically here. So the equation was originally V is equal to Kr prime times A power A, where A is the order, A small is the order. Now, if you use the idea of the initial rates, so at the beginning of the reaction, we have V naught, which is the initial rate, is equal to Kr prime, the rate is constant, times the concentration of A power A. Now taking log of both sides now, if you take, and this is important skill that you need to do in this course, in many of the questions, taking the log of each side, that means you have to take the log V naught is equal log this term, Kr prime A power small a. There are two rules in log that you need to remember. So some just rules for log, and it also applies for the lem as well. Okay, so as you might know, first of all, we have log xy is actually can be written as log x plus log y. We have another one which is log x over y. This actually equals log x minus log y. Okay, we have another rule that says log x power, let's say a, this a goes to the outside and this becomes log a log x. So we're going to use these rules. This also applies to the lem. So lem x power m, for example, it's equal to m ln x. So we're going to apply these rules as we go here. So just remember those, okay? Now let's go back to our equation here. It says log v naught is equal log a prime times a. So we have two things here that we need to separate, kr prime and a. So this becomes as, going back to the question, log v naught is equal log kr prime plus log consideration of a power a. I can apply the exponent rule here to the last term, and this becomes as log v naught is equal log kr prime plus a log concentration of a. Now this is the equation I've been talking about. This takes the form that is y is equal mx plus b here, where y is the log v naught, x is the log a, m is the slope of this equation, and log k prime is actually your intercept. So if you plot this in Excel, whatever, if you plot log the initial concentration, which is a variable, it takes so many numbers, versus the log concentration here, you're expecting a straight line the slope of that straight line is equal to, and the slope of that line, sorry, something is wrong here. Okay, I'm gonna get a straight line here where the slope of that straight line is equal a, which is the order, and the intercept here is your log kr prime. So if you have a value, you can take the antilog of that value and you obtain kr prime. So we're going to use this today. It's called the method of initial rates. Okay. Now this is what I've been talking about. This is the equation again. Log v naught is equal log kr prime plus a log a naught. So if you plot in the y-axis the log v naught versus log a naught, then you will have a straight line. In this case, the slopes are shown here as just an example, 1 or 2 or 3. So if the slope is 1, this means this is the first order in terms of a, and so on. And to apply this, let's start with this very easy example here before we go to more complicated examples. This example says for the reaction A goes to B, determine the rate law using the method of initial rates. I'm gonna So for this example, it says for the reaction A goes to B, determine the rate law using the method of initial rates. We are having here different concentrations of A and different initial rates. These have been designed or determined by an experiment. So the way to know the order or the rate law for this reaction, I'm going to show you how to do that in Excel. You can actually just copy this if you like from your PowerPoints, and I'd love you to do that by yourself so you can train, you get hands-on in this as well. So I'm going to open my Microsoft Excel, and I'm going to throw the values here, just paste them into the program. Okay, so here I have the values, the A and the initial rate, and if you plot the concentration versus the initial rate, that's not going to give you anything because that's not the idea here. The idea is to calculate log A and log initial rate and plot that. So we're going to have the log A in the x-axis, so I'm going to make a column for log the concentration of A. And that's unitless, of course, log is unitless. And I'm going to make another term for the log the V naught, which is the initial rate, okay? I'm not worrying about formatting at this point too much. So in Excel, you can easily do that by saying equal in the keyboard, and you start typing log. That will give you an options of many functions. You just double click on the first one, and you click this value, and you click enter. You're going to do this again for people who missed that point. So this is equal in the keyboard again, and you start log. You can just double click here and choose this value and click enter in the keyboard, and then you can just drag this down, as you know, to the other values. That's log A. I'm gonna do the same thing for log the V naught. So this is equal again log this number, enter, and drag this down. Just for my values to look nice because they look really ugly, I'm gonna format this in Excel as numbers, and this way, actually this looks much better now. You can control the number of significant figures in Microsoft Excel by clicking on these two buttons here, increase decimals, decrease. You can play with this at home and you learn about it. Now let's plot this log A versus log V naught. Now make sure to understand what you are doing here. You need log A to be in the x-axis and log V naught in the y-axis, because sometimes Excel does weird things. You need to know what you are doing. So I think we're going to be fine if we just go ahead and plot scatter. We choose scatter as usual, and this looks like a nice plot. Now the only thing, there is so much empty space here, so I'm going to just double click on this x-axis. I'm going to change it to from -3 to -2. That should be okay. Okay. Of course, you can You can here play with this and add an X title and Y title and everything. But what we are interested about here is just to see the slope. So if we click on the points and add trend line, you'll have, you choose linear, of course. You put your equation R square value, and that will give you, let's see, this is too small. You can just click on this and change the size. Let's say 14. Sorry, I have to click on the box itself, not only one thing. Let's try this again. 14. Okay. So the slope, so this is y equals 1.9695x plus 5.9286. And the r square is 0.996. So the r square is called the goodness of fit, or the regression coefficient. And the maximum value of the r square, or the best value is unity, so 1. So the closer the value is to 1, the better the fitting is, or the better your data is fit to this linear equation, okay? So we have a nice r square value, but what we are need actually is the slope. And as you see, this is y equals a number times x plus a number. So the first number is your slope, which is 1.97 roughly, and this is estimated as 2. So this is a second order reaction for A. So what I did here, to summarize, I went ahead and I calculated log A and log V naught. I made a curve in Excel, which is log A versus log V naught. I got a graph, and the slope was around 2. Okay, so this is second order in A, and therefore this rate law can be written as V is equal Kr, which is the rate constant, times A squared. And you can calculate now what is Kr actually by taking any of these two values. I'm going to do this for you here on this slide. So if I can calculate, so the rate, I know the rate law is V is equal Kr, rate constant, times A square, Y square, because we just found this is second order. You can take any of these values. Let's take the first raw here, where the initial rate is 5. This is equal to Kr times A, which is 0.0022 square, and therefore Kr is equal 5 divided by 0.022 square. You can do this in the calculator and you find your Kr. In units of, it's going to be molar second minus 1, and I'm going to show you the units of Kr very soon. So that's the method of initial rates. Now let's move on to this example, which might be a little more complicated, but it's the same idea here. But now we have two reactants that we need to deal with, not only one reactant. Now this question says the following data were obtained on the initial rate of binding of glucose to the enzyme hexokinase, and we have concentrations of glucose. We have 3 experiments. It's not only one experiment that we did, where we determined the V naught. The data are shown horizontally, so you need to maybe think about them and vertically. And the enzyme concentrations were this and this and this. Find the order of reactions with respect to glucose and the hexokinase and the rate constant. So 3 things that we need to determine here. The rate order, the reaction order in terms of glucose and the enzyme, and also the rate constant. So let's think about this step by step here. First of all, we have 2 things, which is the glucose and the enzyme. So I'm gonna write this down. So first of all, we have 2 things here. We have the glucose and the enzyme. So glucose is reacting with the enzyme, which is the hexokinase, to form whatever products. Maybe it's the glucose enzyme product. It's only one product. We don't care about the product in kinetics. We just focus on the reactants. And therefore, the rate law, if I ask you to write the rate law for this reaction, you're going to say V is equal to some rate constant multiplied by the concentration of the glucose, just referring here to glucose with the G, power whatever power M, and then multiplied by the concentration of H, which is the enzyme, power N. You can call this whatever you like. You can call the HAE, or you can change these letters here the way you like. Now let's use the isolation method here first to apply the method of initial rates to find the glucose first, and then I'm going to show you how to find it for the enzyme. So let's focus only here on the first experiment, which is A, where we have a fixed concentration of the enzyme, but we are changing the concentrations of the glucose, and therefore using the isolation method, this tends to be V is equal to Kr prime now times G power M, where Kr prime is actually equal to the old Kr and this, because I'm fixing H as constant. So using the isolation method, I'm keeping H as constant, which is actually, if you look at the table for the data points for A, H, the enzyme is constant, and therefore Kr prime in this case will equal to the old Kr, the original one, multiplied by H power N. Then here I have an equation. It looks easy. I can take logs for both sides for this equation and make a graph to determine the value of M. Again, M and N are the powers, or the orders, I'm sorry, of the reaction. You can call them whatever you like, okay? You can call them A and B, you can call them J and C, whatever you like. So here I have log V is equal, it's going to be log Kr prime plus M log G, and I showed you how to obtain this equation before. So that means a graph of log concentration, log V versus log the concentration of glucose should give a straight line with a slope equals to M and intercept equals to log Kr prime. So from that you can get the slope for the glucose. You can also get the log Kr prime for this reaction. And we did this here in the next slide. And we found the slope to be actually equals to 1. You can do this in Excel in order to understand it. But somebody did this. He plotted the log, the V naught for the first experiment, and the log glucose, and this is going to be the first curve, the first straight line at the bottom. And also he did it for B and C for the other parts of the question. And whatever we do, it's the same curve, it's the same slope, and the slope is 1. So here we found the M is equal 1, and therefore this is a first order reaction in terms of A. So this is easy now. We solved the first problem, we found N. Now we're gonna go and do N. So the way you do this is I'm gonna actually focus in this equation now. I'm gonna benefit from this equation, okay? And from that I can calculate M. So the way you do that, we know that the Kr prime is defined as Kr multiplied by the enzyme concentration power, was it N? I think, yes, N. Then we can take both log for both sides here, and this will give you, again, log Kr plus N log concentration of the enzyme. You see how useful this is. Now we can obtain the Kr values. So we have A, B, C. We can obtain the Kr values from the intercept, as I said, because the intercept will give you log Kr prime. You can take the antilog and you determine Kr prime for the first experiment, and for the second experiment, and for the third experiment. And you have also the concentration of H given to you in the question. So you can also in Excel make a new tables for log K prime and log H. You plot this versus that, and you will obtain the n. And also, we found that n, after we do all of this, we found n is equal 1 as well. And we did this already, and it's shown in the book. He's going to give you that equation, and also that equation is giving a slope of 1. And therefore, this is a first order reaction in terms of glucose, first order reaction in terms of the enzyme. So this is in total a second order rate law. The last thing is you need to find the rate constant. You can go back and apply. You can the log you can apply. You can take it from the intercept of this graph, the log KR. You can get it from the intercept of this graph. This is only one graph, okay? This is only one graph. You cannot do any more. And the intercept, from the intercept, you can get the value of KR, which is the rate constant of the reaction. So here I showed you how feasible and how good is the method of initial rates to determine the rate, to obtain very good information on the rate law, the orders, and the rate constant, and all of that. Okay. Now sometimes the method of initial rate is not that complicated. Actually, you can just look at a table like this, and you determine the orders of the reaction in terms of some reactants. So in this question, it says the initial rates for the 3 experiments for the reaction NH4 plus NO2 minus goes to N2 plus 2H2O. We have 3 experiments, 1, 2, and 3. We have initial concentrations of ammonium ions, which is NH4 plus. We have also initial concentrations of NO2 minus, and we have determined the initial rates for each experiment. Now the rule here says if you double the concentration of something, and the rate law and the rate is doubled, then this is first order. So if you double A and the initial rate is doubled, this is first order. If you double the concentration of A, like if you multiply by 2, and you find that the rate is actually multiplied by 4, which is quadrupled, this means second order. If you double the concentration of A, so if you multiply A times 2, and you find this to be multiplied by nothing, by 2, so if you double the concentration, and the rate you find it to be not doubled, it's the same thing. Sorry, no change. This is not no change in the rate. That means this is 0 order, okay, and so on. So if you look at the tables here, in order to use the quick way, you can just fix one concentration and look at the other. So here I'm going to fix the concentration of the ammonium. So I'm going to look only at the first and second line, so 0.0.1. And here you can say that you can see that the concentration of the nitrites ion is doubling, 0.005 to 0.1. So this is doubling the concentration. What's going to happen to the rate? The rate is also doubling. So this is first order kinetics for the NO2 minus. Now, in order to do it for the NH4 plus, this has to be constant. So if you look at the rows 2 and 3, this is constant now. It's very important that you fix the concentrations of all other species except for the one that you want to know. So this is fixed now, 0.1, 0.1. Now what's happening here? This is 0.1 going to 0.2. This is good. So when I double the concentration of NH4 plus, what's happening to the rate? It's also doubling. It's 2.7 going to 5.4. This is double the amount. That means it's also first order for NH4 plus, and therefore this reaction can be written, or this rate law can be written as easy as rate is equal rate constant Kr multiplied by the NH4 plus power 1 multiplied by the NO2 minus power 1, and therefore it says you can omit the 1. And from that you can calculate the value of Kr easily. You can take any of these experiments, number 1, 2, or 3, any of the rows. You can plug in the number of the initial rate and the concentration of NH4 plus and the NO2 minus to determine the value of Kr. So for example, I'm gonna do that for you here. For the first experiment, 1.35 times 10 power minus 7 is equal Kr multiplied by the NH4 plus, which is 0.1 power 1 multiplied by 0.005 power also 1, and an equation with one unknown. You can also determine easily the value of the rate constant. I will leave you to do this as a homework. This was a kind of more complicated one, but this one you have to fix the concentrations of the things of all the species except the one that you need. Now, what if we need to use to determine the method of initial rates mathematically? I'm going to show you the long way to do it, and this is if you can do it by just looking at the table, that's good. If you cannot do it, you have to do it mathematically. And the way you do this is you write two equations at least for the species that you are interested in. So for NH4 plus in this example, the first equation is that the rate is equal to rate constant multiplied by NH4 plus power m. I'm going to start again here as if I don't know I have no idea about the values of m and n, so I'm going to start again. So for experiment number 1, we have a value of 1.35 times 10 to the minus 7 is equal Kr, which is constant, it does not change, times the concentration of NH4 plus, it was 0.1 power m. I don't know m yet. And this is 0.005 power n. Now for I have too many unknowns here, m and n and r, so I need another equation. The other equation I can take it from the experiment number 2. You can take it also from 3, whatever you like. But this is 2.7 times 10 to the minus 7 is equal Kr again. Kr does not change. It's the same thing as at constant temperature. This is now the concentration of this is 0.1 again. Power m times the concentration of that is 0.01 power n. The best way to do these two equations is to divide the big divided by the small, okay? So you divide 2 divided by 1 and big by the big by small, I mean the values, okay? So this is 2.7 times 10 to the minus 7, this is 1.35. So let's divide 2 by 1. So if you do that, you're going to have 2.7 times 10 to the minus 7 divided by 1.35 times 10 to the minus 7 is equal Kr for the second equation, which is 0.1 power m times 0.01 power n divided by Kr. The first one was 0.1 power m, 0.005 power n. Many things cancels out, which is good. The Kr goes with the Kr. This goes with that. Therefore, we are left with 2.7 times divided by 1.35 is 2 is equal 0.01 divided by 0.005 power n. If you know simple mathematics, this should be equal 2 is equal actually 0.01 divided by 0.005 all power n, and this actually equals 2. So 0.01 divided by 0.005 is 2 power n. So there is a rule in mathematics that says if the bases are equal, then the power should be equal, and therefore this will give you n is equal 1. So this is the same result I found before, but this one is the long way here. You can use this to determine, to solve maybe some questions that actually difficult to just obtain by looking at the table. Okay, now we finished talking about the method of initial rates. Now let's move on and talk about the integrated rate laws and the differential rate laws. Now the differential rate laws are actually the ones who we've been talking about since the beginning of the chapter, but these laws, they're not actually very practical to solve kinetics problems. That's why we need to integrate these laws and obtain some formulas that makes us easy to determine. Before we start, we define something called the half-life of the reaction, which is the time that takes for the concentration of a reactant to be half of that initial concentration. So the half-life does not mean the half time of the reaction. So there is a reaction that takes 160 minutes. The half-life is not 30 minutes. That's not the definition of the half-life. The reaction is 1 hour. If the reaction is, let's say, take 10 days, half-life is not 5 days. The half-life is the time that takes. It's the time that takes the initial concentration to be half that initial halved. So if you're starting with 2 molars of something, what time is the reaction? Is the concentration becomes 1 molar? This is the half-life of the reaction. Okay. Now we're gonna take 3 examples, which is the first order reaction, second order reactions, and 0 order reactions. And you can apply this to any other reactions that you might be interested about. But these are the most common and the most common in nature. So I will show you how to derive these equations, okay? And the derivation is not required at this level of your course, but you just need to know where these equations came up from. So I'm going to do the derivation for first order reactions. So for first order reaction, I'm going to we have a simple reaction where A goes to products, and I know that the rate of this reaction is minus dA over dt, because the A is disappearing and therefore the rate of it is minus. Okay, and therefore I define the rate of the reaction is equal to minus dA over dt. So it's the difference in concentration of A over the difference in time. And I also know that I can write the rate is equal Kr multiplied by the value of A power 1. And why 1? Because I already assumed from the beginning that this is first order reaction. Okay, so I have 2 formulas here for the rate. I'm gonna equal these and I'm gonna play with them till I get to integrated rate law. So based on this, I have minus dA over dt is equal to Kr multiplied by the A. The first thing you notice here is that you have concentration to the left and concentration to the right, and this is not good. You need to combine things together, and this is called arranging the variables here. So I'm going to rearrange this equation to be minus dA over the concentration of A is equal to Kr dt. This is called a differential rate law. This is actually a first order differential equation that you can use calculus to solve. But because this equation is very simple, what I'm going to do here is I'm going to integrate both sides. So I'm going to integrate this. So minus integral over dA. So I'm going to write this in a better way. It's 1 over A dA should be equal to Kr is constant. I'm going to take it out. Integral of dt. And that will give you, so integral of 1 over A, you know that's minus ln A. So this is minus, I'm going to just make the minus the other side, so make it easy. So this is ln A from A naught, from the initial concentration of A to A, is equal minus Kr times T. Because the integration of dt is time, and that will give you right away your famous equation, which is ln A minus ln A naught is equal minus Kr time. This is the integrated rate law for first order kinetics. It's a very simple equation. Okay, we can use it right away to determine the concentration of a reactant at any time. We can also use it to determine the rate constant and so on. Now, in this equation, the nice thing about it, it actually can be written as in the linear form, which is y equals mx plus b. But before we do that, we need to know what are the variables and what are constants here. So here, A here is your variable. It changes. Okay. This is constant because this is the concentration of the reactant at the beginning of the reaction. It does not change. This is constant as well. and the time is the variable. Okay, time is changing. So you have A and T are changing, and therefore I can rearrange this equation to write it in this way. Ln A is equal actually minus KR time plus ln A naught. And this is your Y equals mx plus b. In this case, if you go and you plot ln A versus time, and this is what we do all the time, we write the time in the x-axis usually in seconds, you should obtain a straight line, but this straight line should go down because of the slope. The slope here is negative, so the slope should be your minus Kr, which is the rate constant for first order reaction. Also the intercept here on the y-axis, you can actually obtain ln A naught from that, but usually what we are interested in is the rate constant Kr. Now, for first order reactions also we can determine the half-life of the first order reaction. I'm going to derive this as well for you here. So the half-life is defined as, very simply, the half-life is the time for the initial concentration to be halved, okay, to be halved. That's very simple definition of the T half, the half-life of the reaction. So where the concentration of A, let's say we are starting with 10 moles. What time? How long does it take for it to be 5 moles? That's the half-life. And therefore we can start with this ln A. It's equal minus Kr, ln A minus ln A naught is equal minus KRT. And to find the T half. Now at T half, we have the concentration of A is equal half A naught. This is the idea, okay? So we are starting with 10 moles. So let's say, what time does it take to have A naught to be equal 5 moles? So this is the definition here. A is equal half A naught, and therefore I can apply this to the equation. So ln A, instead of A, I say, instead of A here, I said half A naught minus ln A naught is equal to minus KR T. I'm just going to name this T half for now because I'm working with T half. And okay, that's nice. So remember that ln X minus ln Y is equal ln X over Y. So that's ln half A naught divided by A naught is equal minus KR times T half. And therefore, this goes with this easily. We have ln half is equal minus KR T half. And ln half is minus ln 2, as you know. So this is minus ln 2 is equal minus KR T half, and therefore the minus goes with the minus, and you have the equation that T half is equal ln 2 divided by KR. This derivation is required from you because it includes simple mathematics. There is no integration here, there is no derivation. It's just algebra. We are arranging things to go on to the T half formula. Now, the T half for first order reaction, as you see here, there's only ln 2, which is constant, it's 0.69, divided by KR, and therefore T half only depends on the rate constant for first order reactions. It does not actually depend on how much you're starting with material. And that's why it's widely used for archaeology, as I'm going to say here. So T half for first order reactions is ln 2 over K. This is only for first order kinetics. If you want to do the T half for other orders, you might have different formula. But this is widely used for archaeology because the carbon, as you hear, carbon-14 dating is all about determining the age of sculptures or living animals like dinosaurs or whatever, and know how old are they based on the fact that every carbon is available in every spot on Earth, and carbon-14 is the isotope of carbon that is radioactive. It has a half-life of around 5,600 years, so it's a fixed half-life. Okay, then by measuring the amount of carbon-14 in a sample, let's say a rock or an animal or a dinosaur or oil or whatever, we can determine how old is it. And this is not something only archaeologists will do. It's actually, we will do it in an example in this course as well. I'm going to show you how. For second order kinetics, let's do the derivation for second order. The formula is 1 over A minus 1 over A naught is equal KRT. And therefore, we're going to do the derivation just to show you how do you do that again. So for second order kinetics, so again, we are starting with A goes to products. And therefore, the V for this is equal the same thing, minus dA over dt, because the A is disappearing, and we define the rate is minus dA over dt, and there is 1 here, so this is 1, okay? But we can also write V is equal KR multiplied by A squared and Y squared, because I'm working with second order kinetics here, okay? I want to do it for second order. So I'm assuming this reaction is second order. So I'm going to equal these two parts here. I'm going to do the derivation very quickly. Sorry. So minus dA over dt is equal KR A squared. And so I'm just going to stop writing the brackets here for convenience. So this will be this, but rearranging this will give you minus dA over A squared is equal KR dt. You know now what is this part when you integrate this. You know what this part means. This is equal KR dt, but now we need to know the left part. The left part is you integrate 1 over A squared, that's 1 over A. So this is minus 1 over A between A naught and A. This is equal to KR time. And this should give you the famous equation, which is 1 over A minus 1 over A naught is equal KR time without minus. This is the only equation that is actually plus. So 1 over A minus 1 over naught equals KRT. And you can rearrange this equation again in the form of a linear equation. You can just send this term to the right, and this will give you 1 over A, which is the Y, is equal KRT, which is the MX, plus 1 over A naught, which is the intercept. And therefore, if you plot here, if you plot in the Y-axis 1 over A, and time in the X-axis, this could give you a straight line that is going up. Okay, it's going to go up, not down, and the slope of that line will equal to KR. The half-life of that, I will leave you to derive it. It's going to be T half is equal 1 over KR A naught. Please do that derivation. And for zero order kinetics, the derivation is actually much easier than this. I'm going to do it here for zero order. The easiest one is the zero order, because you have A goes to products. The V is equal minus dA over dt, as we always say. V is equal also KR times A power 0. Now why 0? Because I'm working with zero order. And this terms equals 1. And therefore, the derivation now becomes so easy. Super easy, it does not even need calculus. This one is minus dA over dt is equal KR, and therefore minus dA is equal KR dt. Even if you don't know anything about calculus, the integration of dA is equal minus, I'm just going to change the minus to the other side. This is minus KR integration of dt. And that will give you integration of dA is A is equal minus KR time. This is between A naught and A, and this is between time equals 0 and T, and this will simplify to A minus A naught equals minus KRT. This is the formula that you are going to use to solve problem for zero order reactions. Not only that, but you can also arrange this equation to be in the linear form. So there's going to be a minus kr t plus a naught, and therefore this is your y equals mx plus b. You see this is again and again repeating itself. So in this graph you plot the a on the y-axis and the time in the x-axis, and you will find that this is going to be a straight line going down with a slope is equal to kr.